Today we're going to be looking at Gaussian elimination and matrix inversion. So this is a method for solving systems of linear equations. For example, if we had 2x plus 3y is equal to 5 and 5x plus 2y is equal to 7, we could solve this system of linear equations using Gaussian elimination. The method is as follows. Find the leftmost column that is not all zeros, get a non-zero entry at the top of this column, make this entry 1 by multiplying the first row by a suitable number or interchanging two rows. This one entry is called a leading one. Add suitable multiples of the top row two rows below so that all entries below the leading one becomes 0, and we cover up the top row and then apply these steps again. To show you how this method works, let's say we had x plus y plus z is equal to 3, 2x plus y plus z is equal to 4, and x minus y plus 2z is equal to 5. What we first need to do is write the augmented matrix. So all that would be is the coefficients of x, y, and z. So 1, 1, 1, 2, 1, 1, and 1, minus 1, 2. And we include 3, 4, 5 over here. So 3, 4, 5. And this would be the augmented matrix, which we write as A dash B. So now that we have this augmented matrix, step 1 tells us to find the leftmost column that is not all zeros. So in our matrix, that would just be the first column. So 1, 2, 1. Step 2 now is get a non-zero entry at the top of this column. So at the top of this column, we already have a non-zero entry, which is 1, so we don't need to do anything. And we need to make this entry 1 by multiplying the first row by a suitable number or interchanging two rows. As our matrix already has 1 in the top of this column, again, we don't need to do anything. Number 4 is add suitable multiples of the top row, two rows below it, so that all entries below the leading one become 0. So we need to make this 2 into a 0 and this 1 into a 0. To do that, we need to get row 2 and minus it by 2 times row 1. So 1, 1, 1, 3, and then we would get 0, minus 1, minus 1, minus 2. And in this row, we keep the same. And now to make this 1 into a 0, we need to do row 3 minus row 1. So we get 1, 0, 0, 1, minus 2, 1, 2. And now we need to cover up the top row and do the same steps as before. So we find the leftmost column that is not all zeros. That would be this one this time. And we get a non-zero entry at the top of this column. Minus 1 is already not 0, so that's fine. And then we make this entry 1. So that means we need to do row 2 and times it by minus 1. So that would give us the matrix. Now what we have to do is add suitable multiples of row 2 in order to make minus 2 into a 0. So to do that, we have to do row 3 plus 2 times row 2. This gives us 0, 3, 6. Now we ignore row 1 and row 2, and the leftmost column, which is not all zeros, is this. This 3 we need to make into a 1. In order to do that, we have to do 1/3 of row 3. So we have 1, 1, 1, 3, 0, 1, 1, 2, 0, 0, 1, 2. So this last matrix is called the row-echelon form. And that's because it has these 3 properties. One of them being every non-zero row begins with a leading 1. Number 2, a leading 1 in a lower row is further to the right. And number 3, 0 rows at the bottom of the matrix. So now what this matrix reads is x plus y plus z is equal to 3, y plus z is equal to 2, and z is equal to 2. Which is fairly obvious to see that we have z equals to 2, y is equal to 0, and x is equal to 1 as our solutions. But we can continue with this process so that we can read directly the solutions to our systems of equations from this matrix. In order to do that, we must begin with the last row and add suitable rows to each row above to get zeros above the leading ones. In order to show that, let's write down our matrix, which is 1, 1. So what we are going to do is start from the last row and add suitable multiples to each row above it to get zeros above the leading one. So here's the leading one. We need to make this into a 0. In order to do that, we have to get row 2 minus row 3 from it. That gives us 1, 1, 1, 3, 0, 1, 0, 0, and then 0, 0, 1, 2. And now we must make these two ones into zeros. To do that, we get row 1 minus it from row 2 and minus it from row 3. So then we're left with 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. And now this matrix tells us that x is equal to 1, y is equal to 0, and z is equal to 2. This form of the matrix is called the reduced row-echelon form. And that's because it has these 4 properties. Every non-zero row begins with a leading one. Number 2, a leading one is further to the right. Number 3, 0 rows at the bottom of the matrix. Number 4, every column with a leading one has zeros elsewhere. And hopefully you can see all those properties in this matrix. If we do another example, let's say we have this matrix, this augmented matrix, which was 0, 0, 2, 3, 0, 2, 3, 4, 0, 0, 1, 5. So first step is find the leftmost column that is not all zeros. In this case, it would be this column, and get a non-zero entry at the top of this column. So this time, the way we're going to do that is by interchanging row 2 and row 1. So we're going to swap these two around. So we get the matrix 0, 0, 0, 2, 3, 4, 0, 2, 3, 0, 1, 5. Now we need to make this entry 1. To do that, we times row 1 by a half. That gives us 0, 1, 3 over 2, 2, 0, 0, 2, 3, 0, 0, 1, 5. Now we must add suitable multiples of the top row to rows below it so that all entries below this leading one become 0. We don't need to do that in this case because all the entries below the leading one are already 0. So then we can move on and cover up the top row and apply the steps again. So when we cover up the steps again, when we cover up this first row, we now look at 2. We need to make 2 into a 1. To do that, we do a half of row 2. So we get 0, 1, 3 over 2, 2, 0, 0, 1, 3 over 2, 0, 0, 1, 5. Now we need to make this into a 0. In order to do that, we must do row 3 minus row 2. That will get us 0, 1, and 7 over 2. So now we are left with this matrix, which tells us that y plus 3 over 2, z is equal to 2, z is equal to 3 over 2, and then 0 is equal to 7 over 2, which of course is not possible. So this system of equations has no solution. Moving on, we're now going to try find the inverse of a matrix using row operations. So our row operations are, we can multiply a row by a non-zero constant, we can interchange 2 rows, and we can add a multiple of 1 row to another. So everything that we saw when we did our Gaussian elimination. If I now work through an example, let's say we had the matrix A, which is a 3 by 3 matrix which goes 1, 2, 4, 1, 3, 6, minus 1, 0, 1. And we need to find the inverse of this matrix. What we first do is form the augmented matrix. And this time we have I, the identity matrix. So this matrix looks something like 1, 2, 4, 1, 3, 6, minus 1, 0, 1, and then the identity matrix, which would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, to find the inverse of the matrix A, we need to make the matrix now be in the form of IB. So we need to make this side of the matrix into the identity matrix. If we begin by doing that, it's the same process that we saw with Gaussian elimination. So here we have a leading 1, and we must make all these other entries into 0. To do that, we must get row 2 and minus it by row 1, and that's the same. And we need to get row 3 and add it by row 1. When we do that, we get 1, 2, 4 stays the same, 0, 1, 2, and then 0, 2, 5. And these row operations we need to do to the identity matrix as well. So row 2 minus row 1 would be minus 1, 1, 0, and row 3 add row 1 would be 1, 0, 1. If we now ignore this row, we now get to this one, which is already a leading 1, and we need to make this entry into a 0. In order to do that, we must do row 3 minus 2 lots of row 2, and we get 0, 0, 1. Now if we do the same thing with the identity matrix, row 3 minus 2 lots of row 2 would give us 3 minus 2, 1. So now we have reached row echelon form, and we must continue until we get the reduced row echelon form, because then we'd have an identity matrix. So in order to do that, we now must make these entries all 0. So that would happen when we do row 2 minus 2 lots of row 1. So we get 1, 2, 4, 0, 1, 2, 0, 1, 0, and 0, 0, 1. Doing that to the identity matrix, we have 1, 0, 0, minus 7, 5, minus 2, and 3 minus 2, 1. And we now have to make these two entries 0, so that would make us do row 1 minus 2 lots of row 2 minus 4 lots of row 3. So that gives us 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity matrix. And we would get 3 minus 2, 0, minus 7, 5, minus 2, 3, minus 2, 1. So now the matrix is in the form identity and sum matrix B. So inverse of A would be 3 minus 2, 0, minus 7, 5, minus 2, 3, minus 2, 1. And we can check this. If we did A multiplied by the inverse of A, we should get the identity matrix. Hopefully that made sense.